Yes. Yeah, in the last class, we seen about the CMOS VTC characteristics. Okay. So how the VTC characteristics are there? That I think hope you remember that CMOS VTC characteristics. Okay. So today we'll discuss about what we call CMOS parameters. Okay. So CMOS parameters. Okay, we'll discuss. My screen is visible, no? CMOS inverter parameters. What are the parameters? That is VIH, VIL, and noise margin. Noise margin. Okay. So that means for CMOS inverter, noise margin should be high. Suppose like if you consider for inverter circuit, suppose the noise margin is zero point 0.1 means it can allow. Okay. So the noise means what? Unwanted signal. Okay. Unwanted signal. Okay. So I think my screen is visible. Okay. Yes. Okay. Uh, so here we already seen the CMOS circuit. Okay, what is the CMOS circuit? That is two PMOS and NMOS are there. Okay, so this is the PMOS and this one is NMOS. Okay, this is basic CMOS inverter. Okay, so this is the input, and this is Vin, and this is VDD, and this one is output voltage. Okay, let us take V out. Okay, so if you draw the characteristics for the VTC characteristics, so how you will get this is a V out, with respect to what? With respect to Vin. Okay, with respect to Vin, I'm drawing. Okay, so if I draw this, so what I'm getting, this is the, it will start from VDD. Okay, it will start from VDD, and like this it will come, and so we already seen this characteristics. Okay, like this you'll get. Okay, so like this, once again. Yeah, like this you'll get the characteristics. Okay, so that means from here I can say that this one. Okay, this one, this one is nothing but this is the slope. Okay, this is the slope. So here I can say that dv out by dv in dv out by dv in equal to -1. Okay, so this we call as VIL. Okay, input low voltage. Okay, and next here you see here this point, dv out, dv out by dv in equal to -1. This point we call as VIH. Okay, and between this center point is VDD by 2, and this is 0 volts. Okay, and here what happens during this region, NMOS is operated in saturation region, and PMOS is operated in linear region. Okay, and here if you see NMOS is this is VIH. Okay, input high voltage. Okay, VIH. So this NMOS is operated at linear region, and PMOS is operated at saturation region. PMOS is operated at saturation region. Okay, and anyway, this VOH equal to output output high equal to VDD only, and output low equal to 0 only. Okay, output low equal to 0 only. So now I'm going to calculate that is VIH and VOH and noise margin. So what is noise margin? So noise margin is this is NML, noise margin low. Okay, and from this is up to VDD. Okay, this length. Okay, this total length is nothing but NMH, noise margin high. Okay, NMH, noise margin low and noise margin high. Okay, so I'm going to calculate VIL, VIH, noise margin low and noise margin high. Okay, NM, NM, H, noise margin high. Okay. So noise margin high, I need to calculate. Okay. So if you see the calculation for VAL calculation. So VAL calculation, if you see, so here you'll get dB out by dB in, dV out by dV in, that is equal to -1. So in this, NMOS will be in which region? NMOS will be in saturation region, and PMOS will be in which region? Linear region. PMOS will be linear region. Okay. So from this, I can say that ID sat, okay, IDN sat, IDN sat, that is equal to IDN sat equal to IDP linear region. IDP linear region. Okay. Now you substitute this formula. So what is the formula? So that is IDN sat. IDN sat equal to what? Kn by 2. Kn by 2. VGSN minus VTN whole square. This is the drain current equation during the saturation region, and the linear region you take Kp by 2, and 2 into VGSP minus VTP into VDSP minus VDSP whole square. VDSP whole square. Okay. So here now we know that in the last class we already seen what is VGSN. VGSN equal to what? V in, no? In VTC equations we already seen. Okay. And VGSP equal to what? VGSP equal to V in minus VDD. V in minus VDD. Okay. And next VDSP equal to what? VDSP equal to V out minus VDD. V out minus VDD. Okay. So this I am going to substitute in the above equation. So if you substitute in the above equation, so what you are getting? Kn by 2, Kn by 2, V in minus Vtn whole square, that is equal to Kp by 2, Kp by 2, 2 into 2 into V in minus VDD, V in minus VDD minus VTP into V out minus VDD minus V out minus VDD square, VDD uh, VDD square. Okay. So that is VDD square, no? VDD square, and this is the bracket. Okay. Next, what you need to do, you need to differentiate the above equation with respect to Vn. Okay. Differentiate the above equation with respect to Vn. Why? Because we need a V out by Vn, no? So when I differentiate, what you are getting? Kn by 2, Kn by 2. So here you will get so 2 into Vn minus Vtn, Vn minus Vtn, that is equal to what you are getting? Kp by 2, Kp by 2. Okay, Kp by 2, and this is UV formula. This is nothing but UV formula. Okay, U into. So this is U and this is V. Okay, UV formula you know. So U into dV in minus VDD minus VTP into dV out by dV in next plus plus 2 into 2 into V out minus VDD. So V in is equal to what? 1 only. So remaining all are constants only. Okay. Remaining all are constants minus with respect to that, no? So 2 into V out minus VDD into dV out by dV in. dV out by dV in. Okay. dV out by dV in. Okay. So this I differentiated. Okay. And next what I can write? So here Kn into, so anyway 2 get cancelled, no, all the things 2 get cancelled. So in all things 2 get cancelled. So once again I am writing Kn into Vn minus Vtn, that is equal to Kp into uh, so what you will get, Vn minus Vdd minus Vtp into dv out by dv in plus v out minus vdd minus v out minus vdd into dv out by dv in dv out by dv in. Okay, so dv out by dv. So here what I am doing means kn into, okay, kn, one second, kn into, okay, mm, okay. So I'm substituting dv out by dv in equal to what? Minus 1, no? dv out by dv in equal to what? Minus 1, no? That I am substituting. Okay. So when I substitute, what we will get? Kn into v in minus vtn, that is equal to kp into, okay, kp into, so when you substitute, what you will get? Minus v in plus vdd plus vtp with minus I'm just means multiplying, okay, plus v out minus vdd mm, minus vdd mm, minus vdd plus v out minus plus means plus v out minus with minus I substitute minus multiplied minus vdd okay. So here one vdd get cancelled, okay. So next what I need to do, just v input you take common. If you take common, what you are getting, kn plus kp, just I am taking common, that is equal to so kn plus kp. So you bring v in one side, okay, v in one side, okay. So here plus kn into vtn, no, you bring this side, okay, kn into vtn minus minus kp into vdd, this one, kp into vdd, okay, minus kp into vdd, okay, plus kp into vtp plus two v outs are there, no, so 2 kp into v out, 2 kp into v out, okay. So that means v in equal to what? V in equal to so I can write 2 kp into v out plus vtp minus vdd plus if I consider, that means here yeah, one second, mm, okay, one second, yeah. So v in equal to kn into vtn minus kp into vdd plus kp into vtp plus 2 kp into v out divided by kn plus kp, okay. Now you divide both numerator and denominator with kp, okay, both numerator and denominator with kp, and wherever you get kn by kp, consider this as kr equal to what? Kn by kp, kr equal to what? Kn by kp. So when you substitute, what you will get, that is v in equal to what? VIL equal to 2 into v out, 2 into v out. So kp you multiplied, that means here kp by kp means 1 only you will get, okay, plus plus uh, plus VTP you will get, okay, plus here, see here, divided by KP means what? You will get VTP only, okay. This is VTP minus divided by KP means minus VDD only. Here you will get Kn by Kp. That means what? Here you can write as Kr into Vtn divided by 1 plus Kr, 1 plus Kr. Okay. So this is my VIH, input low, input low equation. Did you understood how I am calculating VIL? Any doubts or any queries? Your response so that I will move forward. Hello, are you available?
No, sir.
No doubts. Okay, shall I move forward? Shall I move forward? Okay. So next you see, next I want to calculate what VIH. I need to calculate VIH. Okay. So VIH calculation, in the VIH calculation, if you see the curve, okay, NMOS will be linear region and this is VIH. NMOS will be linear region and PMOS will be saturation region. Okay. So that means here, so you need to write that is dV out, dV out by dV in, that is equal to minus 1. Okay. And NMOS will be which region? NMOS will be in linear region and PMOS will be in rich region. PMOS will be in saturation region. PMOS will be in saturation region. And you have IDN linear equal to IDP, IDP saturation, IDP saturation. Okay. Here also you write that means IDN linear equal to what? IDN linear equal to IDP saturation, IDP saturation. Okay. So this is what Kn by 2, Kn by 2, 2 into VGSN minus VTN into VDSN minus VDSN whole square. This is equal to Kp by 2, Kp by 2, VGSP minus VTP whole square. Okay. So, so just you substitute that equations. That is VGSN equal to what? V in and VDSN equal to what? V out, V out and VGSP VGSP equal to what? V in minus VDD. Last class we already seen, no? This I took one CMOS circuit and I got this VGSN and VDSN and VGSP. Okay, those only I'm substituting in this equation. Okay, so that is Kn by 2, 2 into V in minus VTN into V out minus V out whole square. V out whole square. This is equal to what? Kp by 2. Kp by 2. VGSP equal to what? V in minus VDD minus VTP. Minus VTP whole square. Okay. Differentiate the above equation with respect to what? With respect to V out. Differentiate. Differentiate with respect to V out. Okay, with respect to V out, if you differentiate, so here what you will get Kn by 2, Kn by 2. Uh, this is UV formula. Okay, so 2 into Vn minus Vtn into dV out by dV in, dV in plus plus 2V out. Anyway, dV in by dV out with respect to dV in means 1 only. Okay, and minus 2V out into dV out by dV in. dV out by dV in, that is equal to Kp by 2 into V in minus VDD minus VTP. 2 get cancel. Okay, here also all 2 get cancel. Okay, so here what you will get, so this is so here if you see, uh, again substitute this dV out by dV in equal to minus 1. So what you will get, Kn into minus Vn plus Vtn plus V out plus V out plus V out. Next what you will get, uh, plus V out. Okay, plus V out plus V out you will get. Okay, plus V out, that is equal to Kp into V in minus VDD minus VTP minus VTP. Okay, so from here, so bring Kp V in on one side. Okay, so that is Kp into V in, Kp into V in, uh, Kp into V in. One second. Mm, yeah, this one you bring it to this side. So that means Kp into V in plus Kn into V in. That is equal to what? Kn into Vtn plus 2Kn into V out. 2Kn into V out is there, no? 2Kn into V out plus Kp into VDD plus Kp into VTP. Okay. So that means here divide. So from here, what you will get, Vn equal to Kn into Vtn plus 2Kn into V out plus Kp into VDD, Kp into um, one second, Kp into VDD plus Kp into VTP divided by Kn plus Kp. Kn plus Kp. Okay. Divide both sides with Kp. So what you will get, that is VIH. Both numerator and denominator with VIH. So here first you write VDD. Anyway with Kp you are dividing. VDD plus here VTP. So anyway Kp cancel. Here you will get VTP. Okay. And next plus Kn by Kp equal to what? I am considering as Kn by Kp equal to Kr. Kr. Okay. So here this is 2Kr. 2Kr V out plus plus what will get, VDD Kr into Vtn, no? Kn by Kp, Kr into Vtn. Kr into Vtn divided by 1 plus Kr. 1 plus Kr. Okay. So this is you got for VAH. You got for VAH. Okay. So that is VAL and VAH. Okay. You need to calculate VAL and VAH for this. Okay. So for symmetrical CMOS, okay, this is the difficult. This much of formula is difficult to remember. Okay. So for symmetrical CMOS, what is the formula means? You need to consider some approximations. Okay. For symmetrical CMOS, you need to consider VTN. That is a VTN equal to VTP, and Kr equal to Kn by Kp, that is equal to what? 1. Kn by Kp equal to 1. So here you will get VIL equal to, after approximation, 1 by 8 3 VDD minus plus 2 VTN you will get. Okay. And VAH equal to 1 by 8, 1 by 8, 5 VDD minus 2 VTN. So these are the approximations. Okay. So these are the approximations you will get. Okay. And what is NMH? Noise margin high equal to, that is VDD minus VAH. VDD minus VAH you will get. Okay. Noise margin equal to what? VDD minus VAH. Okay. So if you see this one, NMH. Okay. NMH equal to, this is NMH. Okay. What is NMH? VDD minus this difference. VDD minus VAH. For getting the noise margin low, you need to calculate VAH also. Okay, you need to consider that symmetrical CMOS and you need to consider VAH. Okay, and NML equal to VAL only. Okay, VAL minus 0. NML equal to VAL minus 0. This is equal to what? VAL only. Okay, input low. Input low means here you see. So NML equal to what? NML. Noise margin low equal to you are getting VAL only. From the curve itself, you are getting low only. Okay. So like this, you need to calculate VAH and VAL. Okay. Yes. Any doubts? Any doubts or any queries? Waiting for your response. Tell me. Any doubts or any queries? Hello. Are you there?
Yes, sir.
Okay. Shall I move forward? Shall I move forward? Did you understood this the derivation and how to calculate the noise margin for this CMOS inverter? Noise margin low, noise margin high, and VAL, VAH. Shall I move forward?
Okay, sir.
Okay. So next we'll see the next we'll see the how to calculate the propagation delay of the CMOS inverter. Okay, how to calculate the propagation delay of CMOS inverter. Okay, so just we'll discuss this and we can wind up. Propagation delay. Propagation delay of CMOS inverter. Okay, 1 second, I will open this PPT. Think or otherwise I will open this. Yeah, first we'll see the propagation delay of CMOS inverter. So what is this propagation delay of CMOS inverter means? Suppose let us take one CMOS inverter. Okay, let us take one CMOS inverter. So PMOS has pull up and NMOS has pull down. So this is VDD and this is ground, VDD and ground, and this is PMOS. This is my PMOS and this is my NMOS, PMOS and NMOS. Okay, input is connected like this. Okay, so input is connected like this, and here you have some capacitor. Okay, capacitor is connected like this. Okay, so capacitor is connected to ground. Suppose if you are giving like this signal. Okay, if you are giving like this signal, so what happens means first initially like so here capacitor will be like output will be you are giving input low, no? So output will be what? High. Okay, output will be high, and after that the capacitor will discharge like this. Capacitor will discharge like this. Why? Because you are giving high. Okay, so due to this capacitor it will be discharged, the output will get like this. Okay, capacitor will discharge like this, and after that so this is what uh, so this is discharging via NMOS. Okay, why? Because when you are giving one, okay, when you are giving one, what happens? This will be off and this will be on. Okay, so capacitor will be discharged through, there is no connection between VDD and this ground, so capacitor will be discharged through NMOS. Okay, so capacitor, so here you can write the this is C out, so this is nothing but C out. So my C out discharge through NMOS. Okay, through NMOS my C out will discharge. Okay, after that when it is coming from here to here, okay, when it is coming to 0, so what happens? So this will, so this is the PMOS and this one is NMOS. So now what happens? This will be on and this will be off. Okay, what happens? Capacitor will be charged. Capacitor will be charged. So through PMOS. Okay, PMOS will be on, no? So capacitor will be charged through NMOS, through NMOS. Okay, so that means so from here I can say that when input goes from low to high, PMOS is off and NMOS will be on. Okay, this is first case. Okay, when input is going from low to high, PMOS will be off and NMOS will be on. So C out get discharged via NMOS. Okay, C out go discharged through the NMOS. Okay, and next what happens when input goes from high to low? Okay, high to low, PMOS is on and NMOS will be off. So what happens? C out will be gets charged via PMOS. Okay, CMOS will be charged via PMOS. Okay, so what happens if you draw the actual waveform? So how it will look like means, one second. Here, if we see the normal waveform, so how it will look like means here I am drawing. This is the, one second. Here I am drawing. This is input voltage. Okay, let us take this is input voltage. Okay, input voltage, and with respect to time I am drawing. Okay, so practically that is not sharp, it will be have some curve like this. Okay, so here it will start from where to means VOL, output low. Okay, this is practical waveform. Okay, and here this will be increased like this, and it will be constant, and it will be decreased like this, and it will becomes constant. Okay, and this is nothing but it is coming to 50%. The signal is coming to let us take this is nothing but V 50%. P input 50%, and this is nothing but VOH. Okay, VOH, VOH. Okay. Now, if you see the output waveform, if you see the output waveform, so this is the output waveform V out. So how it will look like means here initially when input is low. Okay, as per inverter, so it will start from where VOH. Okay, it will start from VOH. So it will be constant. It will be constant till it reaches the input reaches 50%. Okay, input reaches 50%. After input reaching 50%, it is going from where to where? So height low to high. Okay, low to high means here what happens? This will be discharged through this capacitor, through this capacitor. Okay, and after that here here if you see this, this is nothing but VOL, output low. So the capacitor will discharge and make constant. And when the input is going from high to low during this 50%, during this 50%, again what happens? The capacitor will charge. Capacitor will charge like this. The capacitor will charge. Okay. So that means here, if you see the if you see the output with respect to 50%, so if you draw the output with respect to 50%, so here if you see the output with respect to 50%, so here this is the output with respect to 50%. Okay, so here if you draw, that means this width, let us check this width, which width, this width, this width is nothing but propagation delay. Okay, that is we can call as tau. Okay, tau tphl. So tphl is nothing but when it is going from where to where, high to low, output is going from high to low. Okay, that is nothing but propagation delay from high to low. Okay, and next if you see here this point, so from where to where, this point, this one. Okay, so this delay is nothing but we can call as tau propagation delay, low to high, low to high. Okay. So what is average propagation delay? Average, one second. Average, average propagation delay, average propagation delay, that is equal to what? Let us take tau p equal to what? Tau propagation delay when it is going from high to low plus tau propagation delay when it is going from low to high divided by 2. So this is the average propagation delay. This is the formula for average propagation delay. Okay. So how to minimize this propagation delay? Okay. So how to minimize this propagation delay means there are some steps are there. Okay. So how to minimize this propagation delay? How to minimize this propagation delay means here by decreasing the load capacitance. Okay. One is by decreasing the load capacitance. By decreasing the load capacitance or by minimizing the size of the integrated circuit. By minimizing the size of integrated circuit IC. Okay. By increasing the width of MOS transistor known as gate sizing. Okay. We can minimize the propagation delay by increasing width of MOS transistor, MOS transistor known as gate sizing, known as gate sizing, gate sizing. Okay. Uh, or by fault voltage swing. Okay. By using full voltage swing, full voltage swing. So what is this full voltage swing? So when the full voltage swing will be good means when VOL equal to 0, so are connected to ground, or VOH should be equal to VDD. This is full voltage swing. Okay. Or by implementing circuit by pull-up network. Okay. By implementing by implementing circuit with pull-up network. Pull-up network. Okay. So like this, we can minimize the propagation delay. Okay. Hope you understood. Any doubts or any queries in this today's session? Hello. Anyone?